We move to the module 4 about a protocol. Let me set it here. So in the module 4 is about everything about protocol. So by the end of this module, you are able to describe the function of the core TCP/IP protocol, identify how each protocol information is formulated. Sorry, is formatted in the TCP/IP message, and secure network connection using the encryption protocol, configure a remote access connection between the device. That one will work with the lab, and employ the various TCP/IP utility for the network discovery and troubleshooting. So just remember that for every communication, you always have to follow the set of the rule. You always have to follow the set of the rule here. Think about if I want to communicate with you, we have to agree on the same language here, right? So if I speak in Vietnamese and you speak in English, we have no way to communicate together. The same with the network communication here. For every network communication, you have to follow the set of the rule. The set of the rule is a standard rule, and everyone has to follow it in order to have the network communication successfully here. And so remember that you have the tools. You have the two model here. Sorry, you have the two model here. The first one is TCP/IP, and the second one is the website here. Let me review a little bit about TCP and the website. Remember that for the TCP, you have the 4 layer. You have the TCP here, you have a 4 layer. You have application layer, you have the transport layer, you have network layer, and you have internet layer, and you have the network access layer. That is for TCP/IP. And the TCP/IP is the most common model you use in the every network communication here. Actually, it's a real model. And you have another model. It is a OSI model here, open system interconnection. So for the open system interconnection, you have the 7 layer. You have application, you have a presentation, you have the session, you have the transport, you have the network, you have the data link, and you have the physical here. So when you matching between the TCP/IP and OSI model, the application layer here is the TCP, the same with the 3 layer in the OSI, the same with application, presentation, and session here. And the transport layer, the same with the transport layer here. And the network layer, the same with the internet layer. And the network access in the TCP/IP here, you have the same with the data link layer and the physical layer here in the OSI model. And remember that TCP/IP is the actual model you use in every communication network communication here. And it is a set of the rule, and you break it down in the layer here. And each of the layer you have many rules, and you have the many things they call it the protocol. Remember that protocol is a set of the rule, and you have to follow here. And the TCP/IP is a suite of protocol, including the TCP, the transmission control protocol, IP, internet protocol, and IP. You can have the IP with 4, or you can have the IP with 6 here. And you have UDP, user datagram protocol, and you have ARP, address resolution protocol, and much more, many more here. And TCP/IP protocol add a header to data inherit from the data from the label above it. That is everything about encapsulation and de-encapsulation. I just told you, right? Encapsulation and de-encapsulation here. And the layer in the OSI model here, you have the layer 7, layer 6, and layer 5. They are the application, they are presentation, and they are session here. The same with the application in TCP/IP here. It's about the data injection. They call it the payload here. So whenever you think of payload, sorry, what is it? Why is it here? Whenever the code is a payload, you understand that it is come from application layer here, right? and it's generated by application running on the source code. You can think about when you open the email or when you want to send a file. There are application here. Right? And for in the layer 4, it's a transport layer protocol. It's normally using the TCP or UDP here. TCP and UDP is two major protocol in the transport layer. We will talk about what the difference between the TCP and UDP later. And normally for this one here, you have to include the port number to identify the receiving application. So let me mention it again. So you can think about this one, right? For the one computer here. For one computer, you only have one physical connection to the internet. You have one physical connection. It can be the copper cable, or can be optical cable, or wireless access here. Right? You only have one physical connection. But you see, at the same time here, you can have many logical connection. It can be the World Wide Web service, or it can be email service, or it can be the transfer file protocol here. So we see, you only have one physical connection, but you might have multiple logical connection here. So in order to know which one belong to which traffic belong to World Wide Web, which traffic belong to the email, and which traffic belong to the file transfer protocol, you have to use the port number. You have to use the port number here. Right? And if you look on the port number, they have the sum of the well-known port number. And you look at the port number, you know what traffic it is. Right? So we think about World Wide Web here. You have the port 80. It's the HTTP for the World Wide Web traffic. So we have the port number 25. You see, they are the email service. And you have the port 20 or 21 here. It is for the file transfer protocol. Right? So that is the purpose. That when you do encapsulation in the transport layer, you have to put the port number here. And the port number is the one who tell you what application it is. Make sense? I don't know if you follow me or not, because all of you online here, it's very hard for me to communicate here. Any question?
No, I'm good.
So now remember that for the transport layer, you add the port number here. Right? So now when you send it down from the transport layer, you send it down to the network layer. Network layer is everything about the IP address here. Right? The IP address here. And from the network layer, you send it down to data link layer. You have to encapsulate it with its header and the trailer. Remember that the data link layer is the only layer. You have a both of the header and trailer here. And normally for this one, they call it a frame. And you have to add the MAC address here or physical address here. And the last one, when you send it out to the layer 1, it's a physical. That when you convert it to the bit number 0 and 1, you can send it to the copper cable, or you send it to the optical cable, or by the wireless access here. So remember, for each of the layers, they have specific name. Right? They have specific name. The payload you have in the application. In the transport layer, they call it the segment here. Segment. In the network layer, they call it the packet. And in the data link layer, they call it the frame. The frame here. So remember, each of the layer, it has a specific name for that. Okay, so remember about the process of the encapsulation. Right? So think about if you have the computer here and you want to access it to the web server. Right? Well, so think about when you open the web browser. When you open the web browser and you enter something here, cisco.com, right? So the process is everything you have to do with the encapsulation and the encapsulation here. That is the payload. Payload is come from application. You see, when you send it down to transport layer, you have something is the port number here. When you send it down to the network layer, you have everything about the IP address here. Right? And when you send it down to the data link layer, you have the MAC address here, and you have the channel also. This is the layer. You have the channel. Channel is for everything about the error detection here. Okay, that is the process of encapsulation. Encapsulation, that means when you send it out. Right? So when you send it to the destination, the process is reverse. So we see when he receives this one here, when he receives this one, the first thing he have to look it up in the MAC address here. He knows that it's sent it to him, right? So you know when it's sent it to him, he strip it off here. It send it up to the network layer. Network layer here, check if the IP address here is correct or not. It's correct, strip it off, send it up to the transport layer. Transport layer look it up for the port number, right? Who look it up for the port number. So if you have a port number 80 here, he knows that this is for the one-way service, and he forward it to the application here, right? So remember that the encapsulation and the encapsulation here always happen during the way from the source to destination here. Okay, so now that is the process. That is the process in when you look into the website model. But for the TCP/IP model, you only have the 4 layer here, right? So you see, you have data come from the application. You have TCP here, come from the transport layer. You have IP here, come from internet layer, and you have Ethernet here, come from the network access. And remember that each of the device here, they involved in the process of encapsulation and encapsulation depend on the highest OSI layer here. Remember that the switch is a layer 2 only. Right? So the switch is a layer 2. It only understands about everything about the MAC address. It has no idea what is the IP address. It has no idea what is the port number. For the router here, it is a layer 3. Layer 3, he understands what is the IP address. He understands what is the IP address, but he has no idea what is the port number. Right? For the firewall, normally working from the transport and application. So firewall is the one who knows what is the port number and what is the application here. Okay. So to make it simple, let me show you some of the simulation here. Okay, so that I do this simulation in the packet chaser here. So the thing about if I want to send the ping message from the 192.168.1.10 go to the 192.168.1.20 here. Let me ping it here. Right? I ping 192.168.1.20. Okay, it goes smoothly, right? So now let's see what happened here. I do the simulation here. Ping, and I switch to the simulation here. Now see what happened here. From the PC, right? From the PC, when you click on this one, this is the ICMP message. That's why you can see what is the layer 3 address here. Layer 3 address, source here, my computer, destination here, .20. Huh? And you can see in the layer 2 here, source MAC address and destination MAC address here. And the layer 1 is the port number, pass Ethernet here. Now see what happened here when you forward it to the switch. Now you see when you forward to the switch, you can click on the packet here. You can see the switch here. It only works with the 2 layer, layer 1 and layer 2. You see, it has no idea what is the IP address. It has no idea what is the port number here, right? So it clearly see how it works with each of the device. Remember, the switch only works with the layer 2. That's why he only understands what is the MAC address here. Now come back to this one. I delete it. I come back to the real time. Now in the case, if I want to ping from this guy here to this guy, not on the same network, right? So you know that in the case of not on the same network, the first step you have to send it to the default gateway. It is router here. It is router here. Now let me do it here. Ping from this. Ping first. Let me ping it first. This guy here is. Ping. This one is 172.31.1.10. I see something wrong with this one. Okay, let me figure out what happened here. 172.31.1.10. correct. 72.21.1.1. How about this one? Yeah, this one. Okay, let me bring the gateway first. Let me see what if I am able to reach a gateway here. Yeah, you are able to bring the gateway here. Let's see if I able to bring that one here. No, you are not able to bring it on one. Okay, sorry. Actually, but this one. Question. Okay, let me fix it later. I come back to you later. So just remember that for each of the device on the network, it operates on specific layer only. The switch are only layer 2, a router only layer 3, and that's why you have no idea what is the port number here. Right? So we can think about this one here. I'll come back to this one. Come back to this one. You can see how it works with the router here. Right? So think about in the case I want to bring it from this guy here. I want to bring it to the phone gateway here. Okay, so we see you have the 3 layer here. Right? Now what next? It's sent to the switch. Switch here only have the 2 layer. Right? Now it's sent to the default gateway. So we see when it's sent to the default gateway, the router is the one who works with the layer 3. That's why again you can see what is the layer 3 IP address. Okay, so that is the way that you have to remember that it depends on the device. Right? The device knows it's a high OSI layer they can read and process. Switch only read at the layer 2. Router layer 3, and the firewall can be layer 4 or application itself. Okay, so when the receiving host receive it, you have to do the process of encapsulation. You can think about you open the envelope and check it and to see if everything correct, send it up to the upper layer. And upper layer again, check the header, correct or not, ship it off and send it up to the upper layer here. Okay, so that I want to review a little bit about the last class here when we're talking about when we send from the on the same network on the remote network here. So now we think about if you look on the topology here, I want to send the message from the PC1 to the FTP server here. And you see this guy here is 192.168.1.110, and this guy here 192.168.1.9, and AA here is the MAC address of PC1, and CC here is the MAC address of the FTP server. So now if you look on this one, remember the first thing whenever you want to send the packet to the destination, the first thing is only to figure it out if the destination on the same network or not. It always has to figure out if the destination on the same network or not. And in order to tell if the destination on the same network or not, it look it up in the network portion. If the 2 computers have the same network portion, you are on the same network here. So think about this one. You have the slash 25 and slash 35 for this one. That means the first 24 bit sorry, it's 24, slide 24. The first 24 bit is in the network portion here. This is a network portion. And the first 24 bit here is a network portion. So we see they are the same. The same, the first step, you know that they are on the same network. Remember that in the case of the same network, you just send it directly together, communicate it directly together. Now, if you look on this one here, if you look on this one, what do you think? What should the encapsulation put in the source IP address and destination here? What do you think? What is the source here? I don't know what you follow me or not. Just tell me. Otherwise, you're really wasting time of me and you here. What is the source IP address here?
Would it be the server?
Now, you want to send from PC1 to the FTP server here. You want to send from the PC1 to FTP server here. What is the source IP address?
110 or 9?
Now, tell me, what is the source here? What is the source?
192.168.1.110.
Yeah, the source here is come from the IP address here, right? So we want to send it from 192.168.1.110 here. So what is the definition here? What's the definition here?
Oh, 192.168.19.
Yeah, .19 here, right? So now, what is the destination MAC address? What is the destination MAC address here? What is the destination MAC address?
A.
No, destination. I'm asking about the definition here.
You were right, just the other one, all the C's.
Yeah, right? Because you know, you are on the same network, right? So we can send directly together. And the definition here is the same as this one. That's why you put the CC here and the source here, II here. Okay? That is the process of encapsulation when you send on the same network here. It makes sense? You just send directly together. Right? That's why the definition here, it is the definition here on the same network. Now, okay, so see, remember here, in the case of the MAC address here, remember one thing you have to remember that the destination MAC address here, it always on the same network. It's only on the same network. You have no way to know what is the destination of the other guy on the remote network here. Now I come back to this one here. Come back to this one. Now I don't want to send on the same network anymore. I want to send it from this guy here to this guy, to the web server here. Now, the first thing you look at, you have to identify that the destination here is not on the same network. Right? The reason that you can tell it is not on the same network because here, your network portion here, 192.168.1, and this guy here, network portion here, 172.16.1 here, not the same. So see, in the case not the same here, what happened? What happened here? You see this guy and this guy here are not on the same network. So what is the first step you have to do? What is the first step you have to do here? If not on the same network, what is the first step?
Man, I think I know this one.
What is
You need to know the other IP address to send it to? Is that it?
No.
No? Okay.
Okay. Now see, that's one thing you have to remember here. During the process of encapsulation, remember one thing here. The IP address always stays the same. The IP address always stays the same. That is always the original source and it's always the original final destination here. So see the source here. You have 192.168.1 110 here. And destination here, you have 172.16.1.99 here. That is the first thing you have to remember, that during the process of encapsulation, the IP address always stay the same. But the MAC address here, it changes step by step here. All right, so see, the first thing you figured out that this guy here is not on the same network. So what is the first step? You have to send the packet to. What is the first step here? And to where is send it to?
Would you send it to the switch or server or router?
Okay. Now, you can think about this one. Right? Normally for the topology here, you have the switch. For the local network here, you have the switch. And in the switch here, you might connect it to multiple computer here. And you have one port you connect to the router here. Remember one thing here. In the case of the same network, you just directly communicate together here. But whenever you want to go to the remote network, you only have one way to send it to. You have send it to the default gateway here. That's the same with this one. I'm standing here in the class and I have many students here. And whenever you want to go to the another classroom, the first step you have to send to the first step you have to go to the gateway here. You only have one gateway, right? So see, even this guy here, whenever he want to go to the internet here, the first step it only go to the default gateway. The first step here go to the default gateway, and the first step here go to the default gateway. That you have to understand about the process here. Right? In the case of same network, that communicate together by the switch here. But in the case of remote network, always remember that the first step here, you have to send it to the default gateway. Absolutely. Right? So now come back to this one. Remember that the source IP address here, you take it from this one. And destination here, you take it from this one here. Okay. Now, you come to the MAC address. What do you think? What's the destination MAC address here? What is the destination MAC address for this one? If you want to send it from this one to this one here. What's the destination MAC address?
A, B, C, D, E, F, 1, 2, 3, 4, 5, 8.
No. Remember that the destination MAC address is only on the same network only. This guy here, not on the same network. And remember that the MAC address here change step by step here.
Is that 2222?
All right. What is it?
Is it all the twos?
No. Yeah. If you look at this one here, right? What is the default gateway of this guy? Where is the default gateway of this guy? Where is the default gateway of the PC one here? What do you think?
The first router.
The router one here, right? The router one here. That's the default gateway of this guy. And it also is the default gateway of this guy. And also is the default gateway of this guy here. You see? This guy here want to go out. He have to go this way. This guy here want to go out. He have to go this way. And this guy here want to go out. He have to go this way. Right? So now, the first step, you know that you have to send to the default gateway. Right? So you have to take the MAC address of the interface here. You put it in the destination, one here. And of course, the source is resolved. It's AI here. It makes sense?
Yeah.
Hello?
Yeah. Yep.
Now, even this guy also, if he want to send it to this guy here also, the source is him, but the destination, it also one here. Because you see, the MAC address or destination here, it only on the same network only, and it changes step by step here. Now, let me clear it here. Let me tell you that if you have here the one here, right? So I think about this one here, B here. I can think about this one is C here. I think about this one is D here. This one is E, and this one F here. I make it short. Remember that each interface of the router, you have the Unix IP address and you have Unix MAC address here. Now, so see, the first step here, you send from here to here. All right. So we see the destination here is 1, and you have the source AI here. That is the first step. Of course, for the IP address here, only take it from the original and destination here for the IP address here. Now, that is the first step, right? That is the first step here. Now we think, when you go to the router open it and look it up, he knows that in order to deliver to the 172.16.1.99, he has the database and he can tell which way is best way to reach the destination. And so after do something with the computation, he knows that in order to deliver it, he have to forward it to the router 2 here. All right? So see, if he want to deliver it from the router here to the router 2, you have to do the encapsulation again. You have to do encapsulation again. So in that case here, so in that case here, you have to replace it here. Oh, sorry. What is it? Okay. So in that case, you have to replace this one here. Where? So we see in the second step here, now the destination is not 1 but the destination here is a C and the source here B. And you see it happen again, hop by hop, change everything here. It makes sense?
Yeah, that makes sense.
This makes sense.
Yes. Now, let me give you another example to really make it simple here. Now think about this one. You want to send a letter. You want to send a letter to your friend. Right? So think about this one. You are in the you are the 10 100 here, 10 sheet Bloomington here, and you send it to the guy here. It is 220 sheet Chicago here, and this name here is A. This guy here A. Right? So now we see the final step you want to deliver this one here. The final step you want to deliver this one here, but they are not on the same network here, right? So we see the first step, you know for sure, you have to deliver it to the USPS Bloomington here. So we see, in order to send it to the USPS Bloomington here, he have meet the guy here at the USPS. His name is B here. Right? So now we see, in order to deliver it here, you have to put the name guy here to A, and you send it to the name guy here to B. Right? So see, when you go to the USPS Bloomington here, you know that in order to deliver it, you have to forward it to the USPS Indianapolis here. Right? So now this guy here to deliver the C, and this guy here to deliver it, receive it the D here, and so on. It go to Chicago, so we have the E, this guy here E, and this guy here F, and you see, and it delivered here. But you see, in order to deliver to the 220 sheet in Chicago here, you only have to keep it to the same. That's why the IP address here is always the same, because each guy here, he have to look it up in the definition here. He know where to forward it, where to forward the letter here. But every step here, the guy here is not the same. 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 So we think about this one. This guy here, you can think about that is the MAC address here. And the address here, you can think about this one. It is the IP address here. That's why you see the IP address here never change. But the guy who handle for every step here, they change it. It makes sense?
Yes. Yes, that makes sense.
Okay. Okay, that's why you see, you have to put the definition here. The first step, it is a default gateway here. And remember one thing here. For that reason here, remember one thing here. Every computer on the same network, you only have to set the default gateway. And the default gateway, it's always the IP address of the interface of the router. And you see, if you look from the IP address of this guy here, he have to configure the default gateway 192.168.1.1. This one also, you have to configure the same default gateway. And this one also, you have to configure the default gateway. It is the IP address of the default gateway. Okay, so now if you look at the process here, remember one thing here. The package that means the layer 3, it's not modified. It always stays the same. That's why the IP address here always stays the same. But But the layer 2 address here, it changed step by step, it changed hop by hop here. So we see it look on this one here. If we look on this one, the layer 3 here, the layer 3 here, layer 3 here, always stay the same, always stay the same. But for this step here, Z is a source and Z is destination here. For this step here, Z is a source and Z is destination here. And for this step here, Z is a source and Z is destination for the MAC address here. Okay, that is the way it works with the encapsulation and the encapsulation here. Now, I think that's all for the idea of encapsulation and de-encapsulation. Okay. Now we move back to the TCP here. TCP is transmission control protocol. It is a protocol in the transport layer. It is transport layer. And when you mention about the TCP, you have the 3 characteristics of TCP. The first one is connection oriented. The first one is connection oriented here. So what is connection oriented? Connection oriented, that means before you send the data from the source to destination here, you have to handshake. You have to handshake with the destination here to know that how many data you can send and if it's available or not. You have to agree on everything. You have to set up the connection before we send it out. That's why they call it a connection oriented here. The second one, it has the sequencing and check sum here. Sequence, that means you see, if you want to send the email, basically you have to break it down into multiple segment here, right? So we have to put it number 1 here, that's the sequence. Number 2 segment here, and number 3 segment here. So when we send it along the way, right? Sometimes this number 1 go on this way, number 2 go on this way, or number 3 go on this way. They're not always on the same way here. So sometimes when they come to the destination, it's not always in the original order. Sometimes you receive number 2 here, number 2 first, and number 1 and number 3 here. So we see by maintaining the sequence number here, look at 2, 1, and 3 here, you can reorganize it back to the original order, right? So we see you have to put number 1 here, put number 2 here, and put number 3 here. That is the sequencing. That's why the TCP here, they call it a reliable, because it can maintain the order of the original data here. And the third one is a flow control. Flow control is that way. Think about that. At one time here, you have the source and you have destination here. You send too many data, and this one is overload. He are not able to handle it. So in that case, he had to tell him, this guy here, I am overload. Please slow down. That's why this guy here have to slow it down. That is the flow control here. It controls the rate of transmission based on how quickly recipient can accept the data. So in general, you have to understand that TCP is something about reliable. And the reason that reliable because that before you send it out, you have to set up the connection. You have to handshake with the destination here. The first thing. The second one is to maintain everything about the sequencing and checksum. Checksum is about the error detection here. And flow control. That means it can adjust how many data you can send it to the destination here. So if you look on the TCP here, you see that is the format. That is the format of the segment here. That is the format of the segment in the TCP here. So you see, you have the source port and destination port here. What is the purpose of port? Let me ask you again. What is the purpose of port here? Why do you need to use a port? Huh? Hello?
Could you repeat the question, please?
Yeah, I kind of missed it. Sorry.
Why do we need to use a port here? Why do we need to use a port here?
Isn't that kind of where they enter or something? Or like where they go through?
Yeah, right. I think that the purpose of port is to tell you what application it is. Right? Because you see that you have one computer here, you only have one physical connection. But on that one, you might have many applications here, World Wide Web or email here. So you have to use the port here to tell which application it is, Right? So think about the port. The port 80 here, you know that is for the World Wide Web service. and you have the port 25 here, you know that is a port for the email service here. All right, so that reason you have to use the port here, and the port work in the transport layer. That is the thing you have to remember it. Now, the second one, you have sequence number here. You have to maintain the sequence number, so you can keep track. You can keep track of every single segment here. You see, you can send number 1, number 2, number 3 here. It's sent it separately, and by maintaining the sequence number here, you can keep track of every single segment here. And it's something when you send it to the destination, and if that destination not receive it, so we can retransmit it to every single segment here. And so you can able to reorganize it into the original order here. And you have the acknowledgement here. That's why it makes TCP reliable, because here, when you send from the source, when you send to the destination here, when you send from source to destination. So when you send it out, you set a timer here. You set a timer. So think about you waiting for the 30 milliseconds here. So within the 30 milliseconds, this guy here receive it and confirm, send it out, the acknowledgement here. ACK acknowledgement. So when you receive the acknowledgement within the 30 milliseconds, you know that you already successfully transmitted to the destination. But if it's greater than 30 milliseconds, but you don't receive the acknowledgement here, you know that something go wrong, something went wrong. So you can retransmit it here. That's why you have to maintain the acknowledgement also. And you have some of the header length, and you have some of the flag here to control the connection. And you have the sliding window. Sliding window is about the flowing control here, flow control. That means how much data you can send at one time. Too much, you have to slow down, and too slow, you have to speed it up here. And you have to check some here about the error detection. And you have urgent point, and you have some option, and pending here, data here. It is the original data. That is the data, the end user one. Right? So see, so instead of the send the original data here, you have many things here. You have to add many things in order to control it here. And all of them, they are header here. Right? So that's why you see, when you get the data from the application here, when you send it down to transport layer, you have to include the header here. So we see header here is a port number, about the sequence number, about acknowledgement number, about a checksum here, many things in order to deliver original data. Any question? Yes.
I have one question, not sure how on topic it is, but what if one of the ports was damaged, like either the source port or the destination port? What would happen then?
Okay. Now think about this one. I'm talking about port here. It's about the logical port, not physical, And because here I'm talking about in the transport layer here. It's a logical port, not the physical, not the port we see in the computer here. Right? So now think about this one here. The question I understand it. So we think about the computer here, right? For the computer, for each of the computer, you have the network interface card here. The network interface card is where you have the port, right? When you have the socket, and you can plug in the cable here. You plug in the cable. The port here is the port here is a physical port. The port here is a physical port. But when you mention the port here, they are logical port. Not the same as this one. See, you only have one physical here. You only have one physical here, port here. But at the same time here, you can handle for many logical connection. You can have a World Wide Web, you can have the email, you can have voice over IP, or you can have file transfer protocol here. They call the port, but the port here is a logical. So we see for one physical port, you can handle for many logical port here. So the port I'm talking here, it is a logical port, not the physical port here. And the purpose, you maintain the port here because you want to know which one belong to the one web service, which one belong to the email service, and which one belong to the voice over IP traffic here. It makes sense?
Yes, thank you.
Okay, welcome. Now, Seth mentioned that the TCP/IP is a connection-oriented protocol, reliable protocol, and the reason that it's a reliable because that you have to handshake from the source to destination before you send the data. And in the process of the handshake, they call it a three-way handshake here. They call it a three-way handshake. Three-way handshake. So what is three-way handshake? The first one here, this one here send a request for the connection. They call the sync here. The sync here. Send the request. I want to set up the connection. Right? The second one here, when this guy responds here, he sends the sync and act here. They send the sync and act. That's the second step. And the third step here is send it about the acknowledgement here. So we see the first step, the second step, and the third step. They call it the three-way handshake. Before every transmission for TCP here, you have to handshake with the destination first. And in the handshake process, you need the three-way handshake. You have to do it, right? So think about this one here. Now, I want to set up the connection, right? So I send the sequence number 100 here. Sequence number 100. That means I want to start from the sequence number 100 here. Now, what happened here? When this guy receive it, right? When this guy receive here, he have to acknowledge it. You have to acknowledge that I will receive the request with the sequence number 100 here. So he sent it out. He sent it out acknowledgement here. So what happened here? Acknowledgement here is 101. Acknowledgement here is 101. 101, that means he tells this guy here, I already received the request with the sequence number 100. And now I expect the next sequence here is 101 here. That's why you see this guy here actually is 100 plus 1. That means he tells this guy that I already received the 100 and I expect the next one is 101 here. And also this guy here also, you also want to set up the connection also. That's why you also have to send out the thing here. The thing here, and for this guy, the sequence number here is 300. So he sent it out the sequence number here 300. Now that is the second step. That's the third step here. The third step here is this guy here received the request from this guy with the sequence number 300 here, right? That's why he had to send out acknowledgement here, and he had to confirm that I already received the sequence number 300, and now I expect the next one it is a 301 here. That's why you have the acknowledgement 301 here, and of course the sequence number here that you send it out. The first one is 200, and the next one is 101 here. Okay, so see, that is a step of the three-way handshake. And remember that three-way handshake is everything starting from the communication, from the TCP communication here. And that way to make it very, very reliable here. Right? You have to agree on everything, and you have to confirm everything here before you send it out. Now, what happened here? So when we set up here, right? See, think about this one. When you already set up the connection here and check three-way handshake here. So that when we send the data here, right? So think about this one. You have the sequence now. It's 101 here, right? 101, and you send now the data. So think about the data now. You have about 2,000 bytes here, right? You have the 2,000 bytes, right? So when you have 101 and start with the 2,000 bytes, this guy here, he have to confirm here. He have to acknowledge that you already received it, and he expect next one is 2,102 here. That means he expects the next one. You have to confirm the correct length of message were received. So remember that in the three-way handshake here, sequence number 100, you acknowledge the 101, right? And sequence number here 300, you acknowledge here 301, right? And after that, you already done with the connection setup, so we can send the data between them. Now, So in the TCP control protocol, you can have the many flag here, right? So you can think about this one. When you look in the normally when you capture in the Wireshark here, when you capture in the Wireshark, you can see what the flag setting here. This one is the flag setting here. So see, you have number one here. Sync here. Number one, that means you set it up. Number one here, that means you set it up. So see, for this one, actually, you have the acknowledgement here, and you have the sync here. You have the sync here. So that is the second step here. You can see that is a second step here. Okay, that is during the process of the TCP connection. You have three-way handshake. You have sync and act here. Right? Now, what happens if you want to terminate it? So in the case of terminate it, you have the fourth step. You have the fourth step. You have to send out the fin here. That means finish. You have to send out the fin or finish here. And this one here, you have to confirm that he already received the finish request from you. He sends the acknowledgement for that. And again, he also have to send out the finish request to you. And the last one, you confirm that you already received the finish request from him. And after that, you can terminate the connection here. You can terminate. That's why they call it two-way handshake. I see. Fin and act, and fin and act here. Two of the two-way handshake when you want to terminate the TCP connection here. Okay, so remember now, let me do it again here. Remember that for the transport layer, you see in the transport layer here, you have the two major protocol. The first one is the TCP. The second one is the UDP. UDP. Remember, TCP it is a connection-oriented protocol. That means before you send the data, you have to handshake. You have to agree on everything with the destination here. Right? That's why it makes reliable. It makes reliable. And for the UDP, it is unreliable. It's unreliable and connectionless protocol. That means you don't have to handshake with destination. Whenever you want to send data, you just send it out. You just send it out. You just send it out. You don't care. You don't care if the destination available to receive it or not. You don't care if the destination overload or not. You don't care if the data come in the right order or not. You don't care about that. That is UDP. That's why it's unreliable and connectionless protocol. You don't have to set up the connection. Okay. So now the question here: why do we use the UDP instead of TCP here? TCP is reliable, but UDP is not reliable. So why you use the UDP here? What do you think? Any idea? Any idea?
Sorry, could you repeat the question? It's a bit loud in here for me.
Now, in the transport layer, you have the two protocol. TCP is reliable, and UDP here is unreliable. The question here: why don't you use TCP instead of UDP?
Because there's no three-way handshake, so it's less reliable.
It's unreliable because unreliable because you don't have to do handshake before you send it out. You just send it out as much as you can. That's why it's unreliable. But the question here is that you know that UDP is unreliable, but you have to use it in some time. Sometimes you have to use the UDP here. So what do you think? Why do you have to use UDP?
Well, for one thing, I imagine it's easier to send out because you can just send it out, and maybe other certain applications may not have TCP just readily available to accept a three-way handshake. That's just my first guess.
Yeah, good. That's good. The thing here is that it depends on application. It totally depends on application. So if you want to something work very fast, you think about if you want to make a voice over IP call, right? The voice over IP call is very, very latency sensitive. you cannot tolerate for any long latency here. So you need everything very fast here, very fast. So in that case, you have to work with UDP here. So UDP is that it's normally working with the application. You need something very fast here. You can think about the voice over IP, or you can think about streaming online here. That is when you work with the UDP. Right? But if the application here, you need something reliable. So think about if you want to send the email, you don't need it fast, but you need something reliable here. You have to use the TCP. Okay, so that's why the TCP and UDP both work in the transport layer, and it depends on application here. Some application work with the UDP, and some application work with the TCP here. And you can see about this one here. So if you look in the encapsulation of the UDP, you see for UDP here, you have the source port, destination port, length and checksum here. Very short, very short header. But when you compare with the TCP here, you have many header here. Sorry, you have many information for header here. That's why it's a long header here. So now what happened here? You see for the data here, right? The data here, when you work with UDP, you have small header only. But for the data here, when you work with the TCP, you have the long header here. That's why UDP is more efficient when you compare to the TCP. So you are able to transmit it faster here. But the thing is that you are able to transmit it very fast, but you don't maintain anything about the sequence number. You don't maintain everything about the acknowledgement number here. That's why you see, when you load during the transmission, you have no way to retransmit it. Or when you send it to the destination here, when the destination here might be the number 3, number 1, number 2 here, you have no way to reorganize it to the original order. That's UDP. Right? So remember that TCP is on connection oriented, it's reliable. Use some application here. And TCP connection is unreliable. That's used when you want something going fast, like voice over IP or video online here. Okay, it makes sense?
Yeah.
Yes, that makes
Yes.
Yeah, it depends on the application. You have to remember that. It depends on application. If you need something very fast, you don't care about reliable. Say voice over IP, video online. You work with UDP. But when you want to send the email, you want to make sure that everything goes reliable here, you have to work with UDP. And UDP faster. It no control for sequence number, no control for the acknowledgement here. You have no way to retransmit it, and you have no way to reorganize it to the original number order. But TCP, you are able to do it.
Yeah, that makes sense.
Okay, so now we already have something about the support. Sorry, about the transport layer here. Remember that transport layer, you have TCP, and you have UDP. So remember that for every transport layer, you have to maintain the port number to tell what application it is. Remember that for TCP, it's reliable. This one, unreliable. And unreliable because you maintain something about sequence number. You maintain about acknowledgement here. And you can retransmit it, and you can reorganize it to the original order. So now that is about the transport layer. So think about, when you think about transport layer, you have to think about the two major protocol. It is a TCP, transmission control protocol, and UDP, user datagram protocol here. That's the two major protocol in the transport layer. Now, when you come it down to the internet, when you come it down to the internet layer, you have the network layer here. Right? So network layer, the most common protocol in the network layer is the IP here. IP, that means internet protocol, and you can have the IP version 4 or IP version 6 here. So the IP, that means internet protocol. Internet protocol here. Protocol. Operate as a network layer of OSI model. It specifies where data should deliver and identify the data source and destination IP address here. The main purpose of of the IP here is because it can identify the IP address here, the IP address. So from the source or destination here, so it can tell you where you route to the destination. That is the main purpose of the IP protocol here. Again, the IP here is unreliable and connectionless protocol. It's the same. It's quite the same with the UDP in the transport layer here. So for the IP here again, it send it out whenever you want to send. It's just send it out. He doesn't care if the destination available to receive it or not. He doesn't care if the packet lost during the transmission or not. He doesn't care if they come in the right order or not. The IP they call it the best effort protocol. Bad effort, that means you try to send it out. You try to send it out as much as you can. Right? And it's not that for that reason here, it's not a guarantee deliver of data and have no session is set up before the data transmission. It works quite the same with UDP here in transport layer. So if you want something reliable, you have to combine the IP with the TCP protocol in the transport layer here. So if you want something reliable, you have to depend on transport layer. You have to depend on TCP here. That's why you see the IP here depend on TCP. If you want to ensure message are put back together in the right order, because the TCP they maintain this sequence number here. That's why you are able to put it back in the right order here. And to ensure that each message is reached to the correct application on the receiving host, you maintain it by the acknowledgement, right? So if you don't receive the acknowledgement during the timeout, more than the timeout time, you have to retransmit it here. And remember, if you want something reliable, IP have no way to do that. It have to depend on the TCP in the transport layer. Okay, so that is the format of the packet here. Right? The packet here. So remember that the process of encapsulation. Right? The process of encapsulation here. You have the data from application. You send it down to transport layer. You have header here. You have header. And here is transport layer. And when you send it down to the internet layer, you have header here. It is for the internet layer. Right? So see the data here. The data here actually it come from the transport layer, right? It send it down. It send it down from transport layer here. The data. When it comes to the internet layer, it come from the transport layer here. And you add the header information here. Add the here. Here everything here is the header information. Right? So the version here tell you which IP version you can have the IP version 4, or you can have the IP version 6 here. Right? And normally if you look on this field here, you have some information, right? So think about you have 0, you have 1, 0, 1. When you convert it to the decimal, you have number 4 here. So you know, sorry, 0 here. You know that this one here, it is version 4. But if you have the 0, 1, 1, 0 here, when you convert it, you have the 6. So we know that is the version 6 here. Right? The second one is a different. What is pronounced? I'm not really familiar with this one. Differentiated service. That is when you set for the priority of service, or they call it the quality of service here. Quality of service. Now, why do we need the quality of service? Any idea? What is the quality of service? I'm not sure I mentioned it before or not. Do you have any idea of what is the quality of service?
Quality of the what?
What is it? Now, think about this one. You have computer here, right? Again, you only have one physical connection to the internet. One physical connection to the internet. So you see, in the one physical connection here, you might have many logical connections. Right? You can have the voice over IP. You can have a one wide web service, or you can have email service here. Now, think about this one. all of them share the same physical connection here. So what happened if you have a congestion? What happened? You have the congestion here. So in that case, you have to set the priority. You have to set the priority for the service here. Right? So in the case of voice OIP here, you need something going very fast. You will need something going very fast. You have to set it a higher priority here. You have to set it for higher priority. But for email here, you don't need to go in part here. So we can set it it's lower priority here. The same when you involve in the traffic here, right? So in the case of the traffic jam, you see you have ambulance, you have the police car. They have a higher priority to go first. The same as this one here. The same as this one. You can set the priority. So this guy is very high, and this guy here is lower. In the case of congestion, this guy here has the right to go first. That's why they call it a differentiated service when you set the priority of the traffic here. And you have the total length. It's what is the total length of the header. You have identification. You have flag here. You have the fragment of set. That means that when you have to break it down into the many fragment here, right? So think about if you have 4,000 here. If you want to send the 4,000 bytes, but when we send it down to Ethernet layer, the maximum is only 1,500 here, right? So we have to put this one at 1,500, and this one 1,500, and this one 1,000 here. So the offset here, offset from this guy to the original one, 1,500. Offset from this guy to original one is 3,000 here, right? So when you look in the offset here, you can reorganize it to the original order here. Okay, one more thing is that is very important here. TTL, that means time to live. Time to live. What is the time to live here? Time to live is the number that you're able to go from the source to destination here. Now think about this one. If you want to send from the computer here to the destination here, so the first step you have to send it to the router here. The second, the router one. The second one you have to send it to router 3 here, router 2 here, and you send it to the destination here. So the time to live is maintained in order to avoid the problem of endless loop here. That means loop forever, loop forever. And sometimes you have something wrong with the routing. You can just ping pong, ping pong, ping pong, loop it forever, forever, and packet stay here forever, and it consumes a lot of bandwidth here. Right? So think about this one here. If you set the time to live here at the beginning, think about it, make it simple here. You set the 16 here. So the time to live work is whenever you reach to the router or the PC here, the time to live decrease by 1. So see, now at the beginning you have the 16. When you reach this guy here, you have the 15. You reach this guy here, you have 14. And when you reach this guy here, you have 13. So whenever time to live drop to 0, the packet will be dropped from the network. So it prevents problem of endless loop here. It makes sense? Now think about this one. If you have something wrong with the routing here, right? When you have something wrong with it, something here, you route to this guy route it to you, this guy again and again and again and again and again. You see, if you don't set the time to live here, it loop it forever. It loop it forever here in the internet, and it consumes a lot of bandwidth and consume a lot of processing time for this guy. That's why they have to send the time to live here. And protocol here. Yeah. Any question?
No, you're okay. Keep going.
Okay. A protocol here to tell you what is the upper protocol ID. So we can tell you that the upper here is using the email service or DNS service or the DHCP service here. And header checksum. Checksum, that means it checked everything here. Header here, it have anything with the corruption data here. Now, the two most major field in the header here, of course, it is a source IP address and it's a destination IP address. That is the address very important, right? Because in order to deliver it to the destination, you have to know where to route it. That's why they are the two most major component field in the header here. You have the source IP address and destination IP address here. And of course, you have the sum of the option and sum of the padding here. And remember here, Data here, everything come down from transport area. Okay, that is now suppose the IPv6 also. The IPv6 the format a little bit different than the IPv4. And IPv6 can accommodate for much longer IPv6 address. So let me make it short here. You have two versions of IP address. The first one is the IPv4. The address is only have the 32 bits in the address, but for the IPv6 you have 128 bits. Okay. Now, if you look in the IPv4, you have 32 bits. 32 bits, that means you have two, you have raised to power of 32, you have about 4 billion address. Nowadays, not enough, right? You see, you have each of you have many devices. You have the cell phone, you have laptop, you have iPad, you have the laptop. Each of them, you need one IP address here. So the 4 billion here is not enough. That's why they come up with the idea of the IPv6. IPv6 here is 128 bits. So when you have raised to the power of 128, you have a huge range of IP address here. And so in the IPv6, there are no fragment offset. Remember that in the IPv4, if the packet here is too large, you have to break it down. All right, for each of the steps in the router. But in the IPv6 here, there are no fragment offset. That means when you want to send from the destination here, you only have to figure out what is the maximum unit you're able to transmit along the way from the source to the destination here before you send it out. You have no way to do with the fragmentation here. Okay, so to make it short, I make it example here. So we have the source here, and we have destination here. So in order to deliver it, you can send it to the router 1, and send it to router 2, and send it to the destination here. So think about this one. This one here, you have the maximum transfer unit of 1,000, 1,000 bytes, and this one here is 500 here bytes, and this one here you have the 800 here. So in order to send from the source to the destination here, this guy here, you have to figure out along the way what is the maximum data unit you can set it here. So if you look on this one, you have 800 here, you have 1,000 here, and you have 500 here. What do you think? Which one work? Which one work here?
500.
Yeah, you have to take from this one here, right? Otherwise, if you take the 800 here, work with this one, right? Work with this one here, work with this one, but not work with this one. Okay, that's the way. That's the IPv6 host here. You have to adjust the packet size to fit the requirement of the network before sending the IPv6 message. Now, so in the internet layer, you have the IP protocol is the more major protocol. You have some other protocol is the ICMP here, the Internet Control Message Protocol. ICMP is used in the case of the text connectivity here. You pick here, if you want to make sure that you are able to reach destination or not, right? That is the ICMP. ICMP is a core network layer protocol that reports the success or the failure of data delivery. So it can indicate the following: when the part of the network is congested or not. That's something, right? So it have the congested, it's sending back to you that you have to take action to slow down. When the data fail to reach destination, also it tell you. And the data have been discarded because of the TTL, it's pi here. TTL, that means when it drop to 0 here, right? And ICMP announced the transmission failure to the sender, but not correct. Remember that it only tells the standard only. It have no way to correct it here. Right? And provides critical information for troubleshooting and network problem. ICMP was 6 or IP6 here perform the function of the ICMP and address resolution protocol on the IPv4 network here. Now you can see you can tell it by the ICMP in the computer when you go to the command line interface, right? So we have the CMD here, common line interface. Now we want to print Cisco.com to see if I am able to reach Cisco.com or not. Sorry. That is it. So we say you have some information. You have some information in the ping also. That is a round trip time. What is the round trip time? Round trip time, that means what is the time it deliver from the source? What is the time it deliver from the source to destination here? Source to destination, and you go back to acknowledgement. That is the round trip time here. So we take the 30 milliseconds to deliver the ping message from the source from my computer to the Cisco.com and go back here. Now you see, you also have the time to live here, right? Time to live here also. So normally it set the 255 here at the beginning. So now you have the 236. So you can understand that I have to go along the way with the 19 router between my computer and the Cisco.com. And remember that when this guy here reaching to 0, the packet will be dropped here to prevent problem and leash loop here. Or you can have one more comment. It's very, very helpful when you want to do with the troubleshooting. It has to say something. Let's go. Copy. Okay, so when you work with the ping, I just tell you that you are able to reach that station or not. But when you work in JSON here, it's tell you step by step from my computer to the destination here. Right? So see, the first step I send it to the default gateway here. That is default gateway. Right? So now go along the way and reach to the destination. Right? And you can check it by the command here. IP. So we see. That is my IP address here, my computer, right? And that is the default gateway here. That is the default gateway. So we see Cisco.com is not on the same network, right? That's why the first step here, it has to deliver to my router on my default gateway here. That's why you see 10.2.2.1, and you look on this one here. That is the first step here, 10.2.2.1. Right? It's really makes sense here, right? Any question?
No.
Okay, now we move to the address resolution protocol. Address resolution protocol work with the conjunction with IPv4 to discover the MAC address of a host or node on the local network. Remember, it's this one. It's only on the local network or on the same network only. That's the thing you have to remember, that on the local network here. And also the maintain the database, map the IP address to the MAC address on the local network. Right? And the IRP address resolution protocol is a layer 2 protocol. Thus use the IP in the layer 3 and rely on broadcasting here. And it has maintained the table It's a database matching between the IP address and the MAC address here, mapping between them. Now think about this one. Let me go back to this one. This one. Let's see. So basically, you see, if you look on the topology, here, right? If you look on this topology, here, now think about if I want to send a message, from my computer here, 192.168.1.10 to the 192.168.1.20. Now you see, this one here on the same network, you see, both of them here have the same network portion here, not on the same network portion, so on the same network. So the computer, the first step, he figured out that the definition here on the same network. Right? So what happened here? He have to do encapsulation. Right? He have to do encapsulation here, and he have to put the IP address. Right? What is the source IP address here? What do you think? What is the source IP address? What is the source IP address here?
192.168.1.10.
Yes, right. You have the 1.10, and definition here you have the 20 here. Right? Definition here you have the 20 here. So for the MAC address here, what is definition? And what's the source here? What is the MAC address definition?
192.168.
No, I'm asking about the MAC address. You remember that you have two types of address here. Layer 3 address or IP address. This one here, layer 2 address, layer 3 address. And the second one is the MAC address. MAC address, that means the layer 2 address here. So see,
PC P2.
no,
I mean
no.
PC P2.
Sorry. Yeah, this one here. Yeah, I make it here. Right. So the definition here, you have to put it here, right? To make it short, I put it here, 1D07 here, and the source you take it from you, right? You have 6EED here. Of course, you need the 12 extra digit, but to make it short, I just put the last 4 digit here. Right. So see, that is the process of encapsulation. Right? If you want to deliver message from this guy to this guy here, you have to encapsulate. The first thing you have to put the IP address here. So when you have the IP address, you send it down to the data link layer. You have to encapsulate the destination MAC address and the source MAC address here, and you forward it out here. Now, that is the case you know. That is the case you already know the destination MAC address here. But sometimes he knows that you want to send it to the 192.168.1.20, but he don't know the MAC address here. He don't know the MAC address of destination here. That is when you use ARP here. ARP is the address resolution protocol. Address resolution protocol is a protocol help you to find out what is the MAC address based on the IP address. Right, so see, now if you know that you want to send to 192.168.1.20, but you don't know the MAC address of this guy, you have to use the ARP here. So in the case of ARP, how it works? ARP at the beginning here, he have to send it out broadcast message. What is the broadcast message? Broadcast message, that means the message send it to everyone on the same network. Send it to everyone on the same network here. So the first step here, he sends an ARP. He send it to everyone. He send to this guy, send to this guy, send to this guy, and send to this guy. And the purpose is that he raised the question, who is 192.168.1.20? He knows he wants to send it to 192.168.1.20, but he don't know if this guy or not, this guy or not, this guy or not, or this guy or not. That is the first step. He sent it out broadcast message. He sent it out to everyone on the same network. And he raised a question here. He who is 192.168.1.20. Now see, when they come to this guy here, not 40, not for him. He just drop the message. This guy here, drop the message. This guy here, drop the message. This guy here, look, I am 20 here, matching you 20 here, right? So when he receives this guy here, he knows that, hey, this guy here want to send it to me. So he had to answer it. He have to answer it. So in that case, you have the ARP reply. Right. The first one is ARP request. Right. So ARP request here. Right. So now he replied. He just sent it to this guy here, and he tells us, I am 192.168.1.20. And if you want to send me, please send it to me on the MAC address here, 1D07 here. Right? So when this guy here received the message, he has something they call it is a MAC address table here. MAC address table. MAC address table is matching between the IP address and the MAC address. Right? So he updated. Oh, so from now on, if I want to send to the 192.168.1.20, I just send it out to the 1D07 here. Okay, it makes sense or not?
That makes sense.
Yeah.
Okay. Now let me do the simulation here, so we can see it very clearly here. So for each of the computer, you only have the local cache, local MAC address table here, matching between the IP address and the MAC address here. So you can check it by ARP and here. So this one here, see, this one here already have the matching between the 192.168.1.20. He already has IP address, and he already have the physical address here. You see, physical address here matching with this one here, right? So now, once he already have in the MAC address table in his cache, he just send it out directly. You don't have to use the ARP here. So you can see, now you can see it here. If you want to send the print here, you just send directly the print, right? And you can go, you see, send the print, right? And send the print. The reason that he send it to only one this guy here because he already have the MAC address of the 192.168.1.20 in his local cache here. Right? That's why he sent it only one here. Now let me delete it, and I want to delete the cache here. I want to delete the cache here in the PC one. So I put it in. Now I check it again. You see, now you have no entry here. Right? So see, now you have no entry here. That means now if you want to send 192.168.1.20, the first step, he have to send the ARP request here. So see what happened here. Do it again. Simulation here. See, what is it? Send it here. So when you click on this one, oh, it's not deleted yet. So I think I have to do it again. Yes, already here, so I have to delete it. So now see what happened here. I go to the simulation, right? And now I just bring here. Bring 192.168.1.20. So you see, what is the message here? Message here, if you look at this message, you can see. If you look at the message here, you can see. Right? If you look at the message here, you can see. I send it from my source MAC address here. But the definition here is not the same as this one. The definition here is not the same as this one. Definition here, you have the 12 digit of F. And in the internet, if you have the 12 digit of F, that means you send it broadcast, you send it to everyone here. You send it to everyone. You understand that? You have, when you send, you have the definition here, all of them have here. And it can tell you here, ARP, right? It's ARP, not the ping message. That means it send it to everyone here. So now, see what happened. What happened next here? What happened next here? It send it to everyone. Send to switch. Now, switch is the one to forward it to everyone. Switch is the one way. See, send it to everyone and send it to everyone. And what is the question here? Sorry, you see, when you see this guy here, not 20, he drop it. This guy here, not 20, he drop it. This guy here, not 20, he drop it. Only this guy receive it here. It makes sense? Very clearly here, right?
Yeah, that makes sense.
Okay, now see what happened here. You see, it sent it here, but not in the correct order, right? So now what happened here? This guy received it. This guy received it, and now he answers this guy here. I am 192.168.1.20, and my MAC address here. Let's see what happened next. So see, this guy sent it back. So what is it? What is it here? Now see, you can clearly see it here. You see here, he sent it here. Now my MAC address here. And I want to send it is this guy here. And my IP address and destination here. So see very clearly, right? You see it very clearly here. So now what happened here? When this guy received it here, when this guy received it, when he received it here, now the next step is just bring it directly to this PCOE. He don't have to send it to everyone anymore because he already update in the MAC address table here. He already updated 192.168.1.20 here, matching with this guy here. So now he already have in the cache. Now he look it up and he knows that he just want to send it here. So now see what next step here. Sorry. Yeah, so see, it's not broadcast anymore. It's not broadcast anymore. And now he already knows the destination already. So see by the simulation here, it can see it very clearly how the ARP working, how address resolution protocol working. Yeah. I go back here. And of course, right now, if you look on this one here, definitely he already updated. He already updated the MAC address of the PC. Yeah, see, he already updated in the cache. That's why he just send out directly. You don't have to send out the broadcast anymore. Oh, what is it? Okay, so it makes sense.
Yeah.
Okay. Basically, if you want to look it up in the cache, local cache here, you have ARP here. Let's see. Now, if you want to send to 192.168.56.255, this one is a broadcast. Sorry. Okay, now that is the IP version 4, and the IP version 6 they have another protocol is network. Hello, someone asked a question. Okay, so in the case of IP version 6, they use the neighbor discovery protocol here. It's quite the same with ARP. So you offer some of the message. You have the router advertisement. You have router solicitation, redirect, neighbor solicitation, and neighbor advertisement. I don't want to go into detail here. It's long way to go if you want to go to detail. Now, you already go along the way, right? You already go along the way so far. You already go along the way so far. You have the transport layer. Go along the way. You have transport layer here. You already have the UDP, TCP. When you send it down to the network layer, you have the IP protocol. You have the ICMP, and you have the combination. Actually, the ARP here is a layer 2, but it's combined with the layer 3 here. Now it moved to the data link layer. Data link layer is the most common protocol is a sorry. Okay, so in the data link layer, the internet is the most important data link layer standard, and normally for every local network nowadays you use the internet here. It's capable of running on the variety of the network media. It doesn't matter if you work with UTP or optical cable or copper cable or wireless here. The Ethernet offers excellent throughput and reasonable cost. It is the most popular. Remember that Ethernet here is the most popular. The most popular network technology used on the local area network. Right? And the Ethernet 2 is now the current standard. So see, remember that when you work with the encapsulation, right? When you work with encapsulation here, you have everything from the application. You have data here, a payload here, right? When you send it down to the transport layer, you have header. When you send it down to the internet layer, you have header here. And finally, when you send it down to data link layer, you have the header and you have the channel. So, right? Remember, header in the transport here normally is a port number, the most common one. And header in the IP here, it is the IP address. And the header in the data link layer here, it is a MAC address or physical address here. And remember, the data link layer is the only layer you have both a header and channel here. That's the only layer you have a channel. So, and the header and the frame check sequence here make up for the 18 byte frame around the data. So we have to add more 18 byte to the original data here. And the data portion in the Ethernet frame may contain from 46 to the 1500 byte. That's why you have the maximum here. Maximum here is a 1500 byte. So in the Internet, if you transmit more than 1500 byte, you have to break it down. You have to segment it here. And the maximum transmission unit is the largest size that the router in the message part will allow the network layer. That's why for every network, you have to follow the FTU here. If greater than, you have to break it down into smaller one. Okay, so we see everything here, right? You look on this one. Okay, so see that is the encapsulation in the Internet here. See, you have the frame check sequence here. Everything about you want to do with the error detection here. Make sure that you have nothing wrong during the transmission here. You have the destination address and you have the source address here. That is the MAC address, and you have the 6 byte. 6 byte, how many bits? If you have 6 byte, how many bits here? 6 bytes, how many bits? What is it? If you have 6, how many bits?
Is it 48?
Yeah, right. One byte is 8 bits here. That's why you have 48 bits. 48 bits here, actually, it is a MAC address here. Remember the MAC address, you have the 48 bits and represent by 12 hexadecisions, right? So that's why you have destination MAC address here. You have the source MAC address here, and you have the Ethernet tie here, and you have preamble here. Preamble, that means to tell you where is the start of the frame. Because you see, when you send it to the net, when you send it to the physical layer, you see everything 0, 1, 0, 1, 0, 1, forever here. So you have something to tell where is the start of this frame and where is the start of the second frame. So from that you can break it down. You know what is the destination, what is the source, and what is the data here. What do you think? Which protocol header includes the source MAC address here? What do you think?
TCP.
Any other question? Sorry, any other answer? Which protocol header includes source MAC address?
Is it IP?
Any other answer?
It's the UDP.
Okay. All of them wrong. Ethernet is the correct one. Now, let me tell you again. TCP here, it is transport layer. It's nothing to do with the MAC address here. Transport layer, you work with the port number, right? The port number. You save. UDP here, transport layer. You work with the port number here. IP, what do you do with the IP? IP, you work with the IP address here. Right? So we think about 192.168.1.10 here. The Ethernet here, it is a data link layer. And the MAC address here is we work with the data link layer only. All right, when you come back here, when you come back to this one here, see, that is data link here, right? And you insert the MAC address here, destination MAC address and the source MAC address here. It makes sense?
Yeah.
Yeah, that makes more sense than before. Yeah.
Now we go with the encryption protocol. The encryption protocol is a mathematical code. It calls the cipher to scramble data into format that can be read only by reserving the cipher only. And the purpose of encryption is to keep the information private. You don't want to expose it to everyone here. And encryption method are primarily evaluated by the three benchmarks. The first one is confidentiality, the second one integrity, and the third one the availability here. You can see they call it a CIA triad here. So confidentiality, that means you have to make sure you are the one who authorized to do it. You have to check everything about the username and password, and you can work with the encryption here. Integrity, that means you have to make sure that the data transmit along the way, no one able to change it, to modify it here. And availability, that means whenever you want it, you are able to do it. Now think about, you have something about redundancy here, right? You can have many things with the availability here. You have redundancy, you can have more router, more switch, or you can work with the rate here, if you know something about the rate, right? So I think it should be better you watch the video here.
The three different arms of the CIA triad refer to confidentiality, integrity, and availability. Confidentiality ensures that information that we're exchanging is confidential or private between the recipients. This is often combined with integrity, which ensures that the information that we're sending to someone else will not be changed along the way. And availability is a fundamental part of IT because we want to be sure that all of our systems and networks remain up and running. Confidentiality is about making sure that data remains private. We want to be sure that only certain information is available to certain people. We often use encryption to be able to do this. If we can encrypt data and send it to a third party, we know that no one in between will be able to read or understand the information that we're sending. We could also use access controls to provide confidentiality. We can make sure that certain people have read access to data and other people may have no access to the same data. This is a common method to provide confidentiality on a server or an operating system. And if you really wanted to stretch the idea of confidentiality, you could look to something like steganography. Steganography is hiding information within another type of media. So for example, you could hide data within an image, send the image to a third party, and then they could extract the data from that image. Anyone else who sees this image just sees a picture. But if you know how to pull the data out of the image, you can take advantage of this confidentiality. The concept of integrity allows us to identify when data may have been changed. This is especially important if you're sending data to a third party because you want to be sure that they're receiving exactly the information that you're sending and then no one in between is changing any of those details. One way to provide integrity is through the use of hashing. We can create a hash based on data that effectively is a fingerprint of all of that information that we're hashing. If someone changes this data in transit, then the hash that we create at the end of the conversation will be different than the hash that we created at the beginning. If you're familiar with asymmetric encryption, then you're probably also familiar with digital signatures. Digital signatures take this idea of hashing to the next step by encrypting that hash with a private key. This allows the recipient to be able to not only confirm that the data has not changed, but the person who sent the data is the original sender. Another common implementation of data integrity is using certificates. We can use certificates to ensure the integrity of a particular server or particular data. And you'll often see one method of integrity defined as non-repudiation, which means that everyone can look at the conversation and ensure that not only has the data been sent without any changes, but the data really was sent by the originating person. Availability is probably one of the most well-known and expected legs of the CIA triad because we always want to have our systems and our networks up and running. This means that we would use some type of redundancy to ensure that these systems would remain available. For example, we might want to have redundant firewalls, and if one firewall was to fail, we have another firewall that we could install to provide this redundancy. Or this might be in more real time using fault tolerance. This is commonly done with RAID arrays, the redundant array of independent disks, where you can have multiple drives running, and if one drive happens to fail, all of the data is still available on other drives. And of course, patching is another form of availability. By patching, we can provide additional stability and close any security holes that may be in a system, thereby keeping those systems up and running.
Okay, so we have the definition of what is confidentiality, integrity, and availability. And we also have the key, and in order to do that, you can use the key here, key encryption. So in the key encryption, it can be separated into two categories. The first one is primary key, the first one is the private key encryption, and the second one is the public key encryption here. So in the private key, they call it the symmetric because they use the same key. Right? You encrypt this one and you decrypt this one by the same key here. But that is the same key here. Right? But in the case of the public key here, so for each one here, you have one single for the private key, and you have the many public key here, and you can send it to everyone. Remember that public key, that means you send it to everyone. So everyone here, if they want to send it to you, they can use the public key, and they can use the public key, and if they encrypt it and send it to you. And remember that you is the only one have the private key, and you are the only one who able to decrypt it. That's why even that along the way, if someone captures the message here, you have no way to get it. So I think we have one more video here.
I need to find the best way to learn math and science.
In private key encryption, data is encrypted by one single key, which sender and receiver know. That's why private key encryption is also called symmetric key encryption, because a single key is used during the both encryption and decryption of data. Here is an example. Tom is sending a lovely message to Mary, and he doesn't want anyone else to see it. He wants both romance and privacy. He wants to encrypt his message. Well, that's easy because Tom shares the same key with Mary. They will use the same key during the encryption and decryption of the data. Here is how it works. First, Tom uses his key to encrypt his message. Now his message is encrypted to scrambled data. No one can read it. When Mary gets the encrypted message, she used the same key to decrypt his message so she can read it in plain text. What happens next? Do they get married and live happily ever after? I don't know. But at least Mary knows what Tom says, plain and clear. Next, I will talk about two methods of symmetric key encryption. The first method is stream cipher. Stream cipher works on a single bit at a time. It encrypts a data on the fly, bit by bit. This method is not much used in modern cryptography. RC4 is the most widely used of all stream ciphers, particularly in software. A block cipher is an algorithm operating on fixed length of groups of bits called blocks. It encrypts the data in certain length, not bit by bit. When data comes in chunks. The usual size of each block are 64 bits, 128 bits, and 256 bits. Some notable block ciphers include DES, Triple DES, IDEA, RC5, AES, and Bluefish, and just to name a few. Private key encryption is a simple encryption method because both parties are using one single key. It's easy to use, but it has a disadvantage. The biggest problem with private key encryption is that you need to have a way to get the key to the party with whom you are sharing data. If someone gets their hands on the key, they can decrypt everything encrypted with that key. If the private key encryption is used for two-way communications, it means both sides of a conversation will get compromised. You may ask, is there any alternative to private key encryption? The answer is yes. It is public key encryption, which is another story in another video. Thank you very much.
This one.
Lucidchart makes intelligent diagramming easy and helps your best ideas become real. Start from scratch.
Hello, this is Sunny. Welcome back. Today, my topic. In public key encryption, two different keys are used to encrypt and decrypt the data. These two different keys are mathematically related. One is a public key, the other is private key. They come as pairs. The public key encryption is also known as a symmetric key encryption because these two different keys are used. In public key encryption, public key is public to anyone, while the private key belongs only to the person who creates these two keys. Here is an example. Tom is sending a lovely message to Mary, and they agree to use the public key encryption to encrypt his message. Remember, public key encryption to encrypt the sender's message starts with the receiver, Mary. Here is how it works. First, Mary creates a pair of keys, one public key and one private key. She keeps the private key and gives the public key to Tom. After Tom writes his message, he uses his public key to encrypt it. When Mary gets the encrypted document, she uses the private key to decrypt it. Remember, the public key method to encrypt the sender's message starts with the receiver, not the sender. The public key is public to everyone, the private key is only known to the receiver. Here is another example. Suppose Bob wants to send an encrypted message to Alice, and they use the public key encryption. My questions are, who creates the keys? Who use the public key and who use the private key? And how many steps are there in the whole process? You can pause the video to think about these questions. Well, here is the answer and all the steps they take in the whole process. Step 1. Alice creates a pair of keys, one public key and one private key. Alice puts the public key in a public key server which anyone can access. Step 2. Alice informs Bob where he can get her public key. Step 3. Bob gets the Alice public key as he followed Alice's instructions. Step 4. Bob writes the message and uses Alice the public key to encrypt it. Step 5. Bob sends his encrypted message to Alice. Step 6, or last step, Alice uses her own private key to decrypt Bob's message. Although Alice's private key can verify no one read or changed the document in transport, it cannot verify the sender. Because Alice's public key is public, anyone can use it to encrypt his document and send it to Alice while pretending to be Bob. In order to prove the sender, they need another technique.
Okay, so I think this guy explained very straightforward. Even the slow, but it's straightforward. And if you want to know something about the digital signal, you can try it from this guy. And you have the IP security also. It's Internet Protocol security, and it right into the two mode. The first one is transport mode, and the second one is the tunnel mode here. And it's a kind of the transport mode. Transport mode that user encrypts everything in the payload here. Right? So you see you have the IP security header and chiller here, and you send it to the IP layer, and you use the real IP address here. That is the kind of transport mode. Transport mode, remember that it only encrypt in the from the transport layer to the network here. But in the kind of tunnel mode here, you see it encrypt everything, and also it puts a new IP address here. It put a new IP address here outside of the whole encryption of the payload here. And you have something about the secure socket layer and transport layer security. Both of them for the encrypting the TCP/IP transmission here. Both work side by side and are widely known as NNL or DSL or DLL. Think about when a client and server establish an NNL or DSL connection, they set up a Unix session, that association between the client and server. Okay, I think it's better you watch this one.
Hey, it looks like we're losing you.
Hello, and this is Sunny. Welcome back. TLS, Transport Layer Security, TLS, are cryptographic protocols that provide security on the internet. Up to today in 2018, SSL version 3.0 is the version most web servers and browsers support. TLS version 1.1 and version 1.2 are more secure versions. The handshake protocol is basically used between a web client and web server to establish trust and then negotiate what a secret key should be used to encrypt and decrypt the conversation. With the protocol in place, an eavesdropper can only see the connection endpoints but cannot read or modify any of the actual data. Thus, it can protect users' personal data and ensure a safe transaction. Many people are asking on what layer of OSI model does the protocol operate? Some people say it is on the application layer because it's just HTTP over secure sockets layer, and some people say it is presentation layer because encryption and decryption operate on this layer. But some argue it's on session layer because the protocol provides point-to-point session security. It is indeed a gray area, and each argument is valid. The OSI model is not a science, and is only a guideline. The handshake protocol is involved with the top 3 layers OSI model, and if we use TCP/IP model, we can simply say the protocol belongs to the application layer. Here is the process how a client and a server uses a handshake protocol to negotiate how to securely exchange data. Step 1. The client sends client hello message that lists information such as SSL, TLL, TLS version, and the cryptographic algorithms and data compression methods supported by the client. Step 2, server responds with server hello message that contains the cryptographic algorithms chosen by the server from the list provided by the client. The session ID, the server also sends is a digital certificate and is public key. Step 3. The client will contact the server's CA and verify the server's digital certificate, thus confirming the authenticity of the web server. Step 3 is basically establishing trust on the web server. Once the client trusts the web server, it will take step 4, client key exchange. With this step, the client sends a shared secret key to be used in the following conversation. The secret key is encrypted with the server's public key. Step 5, the client sends a finished message which is encrypted with a secret key indicating the client part of handshake is complete. Step 6, the server responds to the client with a finished message which is encrypted with the secret key, indicating the server part of a handshake is complete. Once this handshake is done, the server and client can now exchange messages that are symmetrically encrypted with the shared secret key. I hope this video.
Yes, I hope that if you want to look it out, you can find it in the YouTube here. Okay, so we have some of the remote access protocol. Think about if you want to stay from home or you want to access to the switch or the server on the company as a corporate here. Right? So we can remotely access here. You have some of the way you can access it. Right? So you can have the remote access file, or you can use the terminal emulation, or called the remote virtual computing, or you can use a VPN also. And you have some of the remote access file can be the FTP or FTP or DFTP here. So you say as you have something that trivial here is something very fast but not secure. And in order, if you want to do something with secure, you have the FTP here. And you have in the case if you want to remote access, you can use a remote access. You can use a terminal emulation. You can think about if you have the common line interface. Think about if you want to access to the Cisco router or the Cisco switch, you can use the telnet and an edge here. The telnet, remember that the telnet, everything in the plain text only, it's not secure. And edge, that means you have secure shell. You have everything encrypted, so it's much more secure when you compare to telnet. And you have some of the geographic user interface also. You can have use a remote desktop. That is a Cisco proprietary here, or you can use a TVO. Okay, so that is the case. This the core is a terminal emulation here. So in the case if you want to access with the edge or telnet, you have to use the terminal emulation here. This one's a PATI, or you can use a Teleterm, or you can use a CRT here. Okay, so we have the sum of the emulation program. We have remote desktop protocol. It is a Microsoft proprietary protocol here. You can have virtual network computing, or you have out of band management here. That is a dedicated connection between the network administrator and each of the net devices. Okay, and I think the VPN also. The VPN is that you hide everything. Right? Normally, in the process of sending from the source to the destination here, in the process of sending from the source to the destination, you have to do everything with encapsulation. Right? You have to put in what is the source MAC address and what is the destination MAC address here. But the thing is that with the source and destination address, very, very easy to someone to check it out, right? See what is the location here. So that's why they work with the VPN. VPN is that you hide everything inside the tunnel here. That's why he cannot have to check it out for the real IP addresses.
Atera solves IT problems before they even happen.
Hello, and this is on physically existing. But the word virtual means not physically existing, but appear to exist physically. For example, a virtual computer is not a physical computer. You cannot touch it, you cannot feel it, but it not only acts like a computer, but is also capable of performing tasks just like a real physical computer. A local area network, or LAN, is a private computer network that interconnects computers within a limited area such as a home, school, lab, university campus, or office building. VPN is like LAN, but the major difference between VPN and LAN is that devices that are part of a VPN could be anywhere, not limited to a geographical area. They are connected to each other, not over a private network, but over public networks or the internet. VPN use a technology called tunneling, a virtual point-to-point connection. In simple terms, tunneling creates a secure encrypted connection or channel between your computer and other devices within the same virtual private network. With a VPN, an employee can access his own private corporate network while sitting at home or in a hotel. The employee uses his remotely connected private network just as if he were sitting in his own office. Physically, he's outside his corporate private network, but virtually, he's inside. There are some other uses of VPN, such as bypassing internet censorship. Many Chinese use VPNs to get around the Great Wall of China and gain access to the entire internet. Another use is when you use a public Wi-Fi. Your browsing activities on non-HTTPS websites is visible to everyone nearby because your traffic is not encrypted. If you want more privacy, you can connect to a VPN. The local network will only see a single secure VPN connection. All other traffic will travel through a VPN tunnel. I hope this video is
Okay, so that's the VPN. You see put original payload here, right? You put the VPN header, put the header, and you have the IP header here, IPsec header. And that you hide everything. Okay, so we have some of the remote access policy. I think it's already in the slide here. I don't want to go in the detail. You have some of the troubleshooting network issue. Right? You can have next start here to display the TCP/IP static and detail about the TCP/IP component and connection code. Right? Or you can use the chasers or chase route here. Chaser work with the window and the chase route when work with in the Cisco router here. And you see, when you work with the chaser, it's very helpful when you do troubleshooting, right? Because it tells you step by step, and if something goes wrong at any hop, you can take the action to figure it out here. And what else? You have a TCP dump also. It's all used in the case of PH and Unix here. Okay, now we have some problem. It's a common network problem. The first thing is the duplicate MAC address here. So remember that basically the MAC address is unique here, right? And it's burned in address, but somehow they can be spoofed here. They can be spoofed here, right? And basically the mode of the switch is able to detect the problem and produce a helpful error message for you. And in the case of the hardware failure, when the router or the network interface card or other hardware go down, yeah, see this one is full here. You see at one step the packet stop here, so we can take the action for that. And also the ping it is for the network connectivity. Remember that the ping is only for the connectivity to tell you is able to reach destination or not, but it's not tell you step by step by the same as the tracer here. What else? I think that's all. That's all for this for the today lecture. Let's see what you have for the homework here. Any question?
Nope.
I think in this one here, in this lab, I have to tell something here. So for this lab is that to tell you what happened when you have the duplicate IP address here. So basically, you see for every computer, you have two ways to get the IP address. You can go to the open the network and internet setting here. You go to internet. You go to the chain adapter option here. So this is the network interface card. I go to the internet. Right? So I want to change the IP address. I just right click it and go to the property here. So this is where I work with IP 4. I go to the property here. Now see, you have two ways. You have two ways to get the IP address. So you can get it automatically from the DHCP server. DHCP server is the one who gives you the IP address here. Or I can configure it manually here, right? So we can set it manually. But sometimes if you configure it manually or the DCP yourself, sometimes you have the problem of duplicate IP address here. That means that you have the two PC have the same IP address on the same network here. That is the case of the duplication here. Now think about this one. Let me work with the packet chaser here. Let me see if I'm able to do it. Okay, right? So in the packet chaser, I change it to the number 10 here. What happened? We already have someone here, right? Someone here already. Where? You see, for this one here, for in the packet tracer here, it tells you that address is already used in the network. It clearly tells you that it already has the duplicate here. That's why I am not able to do it. Okay, so in the case here, in the case that think about this one here, in the case I want to configure automatically I get it from the DCP here, right? But in my network, I have not configured for the DCP yet. That's why I'm not able to do it. So in the case that the computer not able to get the IP address from DCP server, normally you have something they call the IP pair here. They call it the IP pair here. So see, if you look on this one, where I have to do. Okay, so you have the IP pair address here. They call it the IP pair here. IP pair is automatic private address, automatic private IP address here. So you have everything in the range here. You have everything in the range from the 169 and 254. So we see if you have everything starting with 169, the 254 or something here. That means it is IP pair address. IP pair address means it is the case that you have the duplication IP address, or you are not able to get it from the DCP here. And remember, IP pair with the IP pair address here, you only limited in the local legally. You are not able to go to the internet here, and very limited use of the IP pair address here. Normally, you have nothing to do with the IP pair here. Okay, so I do everything with the other lab, but I think that is the only one I want to mention to you. Okay, so so take your time to do with the lab, and if you have any problem, you can send me an email or you can join my office hour. Any question?
Not at the moment, no.
I'm okay.
No, thank you.
If I have any, I'll email you.
Okay. So let me check the attendance here. Mark, are you here?
Yes,
Yeah, I'm here.
Marty,
Oh, sorry.
are you here?
Yeah, I'm here.
Anyone? Anyone are you here? Kali.
Yeah, I'm here. Sorry.
Okay. Max, are you here?
I'm present.
Max, are you here? Max, no. Jack,
Yes, I'm here.
Smith, are you here?
Yes, I'm here.
Thomas, are you here? Thomas, are you here? No. Okay, so I see you guys on Monday.
Thanks. Have a good one.
All right. Thank you for your time. Have a nice week.
Bye bye.